The core principles of computer science. A deep dive for programmers in the ever-evolving world of technology. Few disciplines hold as much weight as computer science. For programmers and algorithm enthusiasts, understanding its foundation can transform abstract problem-solving into tangible innovation. This guide unravels the essence of computer science through the lens of algorithm design, computational theory, and modern application development. We explore how fundamental concepts shape cutting-edge technologies you interact with daily. Fundamental pillars of computer science theory. At its heart, computer science rests on mathematical rigor and logical precision. This discipline formalizes computation through models like finite automata and Turing machines, providing a framework to analyze what computers can theoretically achieve. Theoretical foundations establish limits and possibilities. Concepts like P versus NP complexity classes define the boundaries of efficient solvability, guiding programmers toward optimal solutions for real-world problems. Computational complexity measures resource efficiency of algorithms, crucial for optimizing performance in large-scale systems. Automata theory studies abstract machines capable of processing inputs, forming the basis for compiler design and pattern recognition. Formal languages defines syntax rules governing programming languages, enabling precise communication between humans and machines. Algorithms, the lifeblood of modern computing. Algorithm design sits at the intersection of theory and practice. Efficient algorithms power search engines, recommendation systems, and cryptographic security protocols that protect digital transactions worldwide. Mastering algorithmic paradigms like divide and conquer, dynamic programming, and greedy approaches equips developers to tackle complex problems systematically. These techniques form the backbone of competitive programming and industrial software development alike. Big O notation quantifies algorithm efficiency, allowing engineers to compare implementations objectively. Understanding space-time trade-offs becomes essential when scaling applications to handle massive datasets. Classic problems like sorting networks and graph traversal illustrate how elegant solutions emerge from rigorous analysis of computational processes. Data structures, organizing information for efficiency. Effective data organization determines system performance. Data structures implement abstract concepts like stacks, queues, trees, and graphs, each optimized for specific operations. Arrays provide fast access but fixed size, while linked lists offer flexible insertion/deletion at the cost of slower lookup times. Choosing the right structure often hinges on balancing speed against memory constraints. Hash tables enable near-instantaneous lookups through clever indexing mechanisms, making them indispensable for databases and caching systems. Their implementation involves resolving collisions through probing or chaining strategies. Trees and graphs represent hierarchical/relationship-based data. Binary search trees facilitate ordered storage, while adjacency matrices efficiently store network connections in social media platforms. Software development lifecycle in computer science context. While computer science focuses on theoretical constructs, software engineering applies these principles to build reliable systems. The lifecycle encompasses requirement gathering, design, implementation, testing, deployment, and maintenance phases. Agile methodologies emphasize iterative development over rigid waterfall models. Continuous integration pipelines automate testing, ensuring code quality as features evolve rapidly. Clean architecture separates concerns through layered designs, improving maintainability. Design patterns like MVC help manage complexity in enterprise applications. Version control systems track changes collaboratively, with Git becoming industry standard for managing source code evolution across teams. Machine learning, bridging computation and intelligence. Modern computer science increasingly intersects with artificial intelligence. Machine learning algorithms process vast amounts of data to identify patterns and make predictions autonomously. Supervised learning trains models using labeled datasets, while unsupervised methods find hidden structures in unlabeled data. Reinforcement learning enables autonomous decision-making through trial-and-error interactions. Deep neural networks mimic human brain functionality through layers of interconnected nodes. Convolutional networks excel at image recognition. Recurrent networks handle sequential data like speech. Ethical considerations now accompany technological advancement. Bias detection, explainable AI, and privacy-preserving techniques become critical as systems impact society at scale. Quantum computing, redefining computational boundaries. Traditional binary logic faces limitations in solving certain problems efficiently. Quantum computing leverages superposition and entanglement to perform parallel computations exponentially faster for specialized tasks. Shor's algorithm demonstrates potential to factor large numbers quickly, threatening RSA encryption schemes. Grover's algorithm accelerates unstructured database searches quadratically. Qubits challenge classical bits by existing in multiple states simultaneously. Error correction remains a significant hurdle due to qubit fragility and decoherence phenomena. Current research explores hybrid systems combining classical and quantum components. Cloud-based quantum services allow researchers to experiment with prototypes before physical hardware matures. Networking and distributed systems fundamentals. Interconnected devices rely on standardized communication protocols. TCP/IP suite forms the backbone of Internet connectivity, managing packet transmission reliably across diverse networks. Distributed systems face unique challenges like consensus building among nodes, handling partial failures gracefully, and maintaining consistency across replicated data stores. Load balancers distribute traffic optimally, preventing server overload during peak demand periods. Content delivery networks cache assets closer to end users for improved latency. Multicast routing allows simultaneous data distribution to multiple destinations efficiently, vital for streaming services broadcasting live events globally. Cryptographic foundations of secure communication. Secure online interactions depend on cryptographic algorithms protecting data integrity and confidentiality. Symmetric cryptography uses shared keys for fast encryption/decryption. Asymmetric cryptography solves key exchange dilemma through public-private key pairs. RSA relies on prime factorization difficulty, while elliptic curve cryptography offers equivalent security with shorter keys. Message authentication codes verify data authenticity, while digital signatures provide non-repudiation capabilities. Hash functions ensure data hasn't been tampered with during transit. Post-quantum cryptography addresses threats posed by quantum computing breakthroughs. Researchers develop lattice-based and hash-based algorithms resistant to quantum attacks. Operating system internals and resource management. Operating systems act as intermediaries between hardware and software, managing resources effectively. Process scheduling ensures fair CPU allocation among competing programs. Memory management prevents conflicts through virtual addressing schemes. Paging divides memory into fixed-size blocks, while segmentation organizes memory by logical units. I/O subsystems handle peripheral device communication, implementing buffering techniques to optimize transfer speeds. Interrupt-driven architectures respond promptly to external requests. Synchronization primitives like semaphores and mutexes prevent race conditions in concurrent environments. Deadlock prevention strategies ensure system stability under heavy load. Emerging trends shaping future technologies. Edge computing decentralizes data processing closer to sources, reducing latency for IoT applications. Autonomous vehicles exemplify this trend, requiring real-time decision-making capabilities. Blockchain technology disrupts traditional record-keeping by enabling decentralized ledgers secured through cryptographic hashing. Smart contracts execute predefined agreements automatically. Augmented reality overlays digital information onto physical worlds, demanding advanced graphics rendering and spatial mapping algorithms. Mixed reality experiences blend virtual and real environments seamlessly. Bioinformatics merges biology with computational techniques, analyzing genomic sequences to advance medical research. Personalized medicine benefits from identifying genetic markers associated with diseases. Education pathways in computer science academic programs typically cover discrete mathematics, probability, and linear algebra as prerequisites. Courses progress from basic programming to advanced algorithmics and systems design. Online platforms offer accessible alternatives for self-paced learning. Interactive coding exercises reinforce theoretical concepts through hands-on experimentation. Research opportunities exist in academia and industry labs working on frontier technologies. Conferences showcase latest advancements through peer-reviewed publications. Specializations range from cybersecurity to game development, reflecting diverse career interests within the field. Practical projects demonstrate proficiency during job interviews. Challenges facing modern computer scientists: rapid technological change demands continuous learning. Keeping pace with evolving frameworks and paradigms requires commitment to lifelong education. Ethical dilemmas arise when developing powerful technologies. Balancing innovation with societal implications becomes increasingly complex as capabilities expand. Global competition drives constant improvement expectations. Maintaining high standards amid tight deadlines tests resilience and adaptability. Environmental sustainability emerges as new concern. Energy-efficient algorithms gain attention as data centers consume increasing amounts of electricity. Conclusion: from foundational theories to cutting-edge innovations, computer science shapes our digital landscape profoundly. Its principles govern everything from simple mobile apps to sophisticated AI systems. By mastering algorithm design, understanding computational limits, and grasping system-level concepts, programmers gain tools to solve tomorrow's most challenging problems today.